Hello everybody, my name is Kalyaan. In this presentation, I will explain my project for the Evolutionary Algorithms module. The task was to build a classifier using genetic programming to predict whether a person earns more than $50,000 per year or not. And this is based on the modified income dataset. I will walk you all through the problem, the data pre-processing that was needed, the GP setup, the training process, the results, and the final model that GP discovered. I have tried explaining this in a very simple language so that the whole process is very clear. So, the main problem we are trying to solve is a binary classification task. The goal is to predict whether a person earns more than 50,000 or less than 50,000 per year. The dataset includes many personal and employment related features such as age, education, occupation, marital status, and many more. These features can influence a person's income level. So the challenge is to use genetic programming to automatically learn a rule or expression that separates high income and low income individuals. The final model must be accurate, interpretable, and be able to generalize to unseen test data for the computation. So now let us talk about the dataset and the pre-processing. To prepare the data for the GP, I first loaded both the training set and the test datasets. I separated the income label from the training set and converted it to 0 and 1. Since most of our features are categorical, I had to apply one hot encoding. This was done to convert them into numerical format. To avoid mismatched columns, I combined the train and test data and applied the same encoding. After that, I scaled all numerical features using standard scalar to the GP so that the GP receives consistent values. Finally, I split the processed training data into training set and a validation set. After pre-processing, each sample had 108 features. I did all this because clean and consistent pre-processing is important because GP works directly with raw numerical values. So for this project, even though I had option of choosing genetic algorithm, I selected genetic programming because it is very powerful for problems where explainability is important. GP does not create a black box model like neural networks. Instead, it evolves mathematical expressions or decision rules that we can read and understand. GP also searches through a huge space of combinations of arithmetic functions, logical operations, and input features. Because this project requires explainability and model understanding, GP was the best choice. It can find relationships between variables that may not be obvious to humans, and at the end, it gives a simple expression that explains how predictions are made. And also, we can fit the assignments required better than the GE for clarity. In genetic programming, the function set and terminal set define what the model is allowed to use. For this project, the terminals are all the input features from feature 0 to feature 107. The function set includes basic arithmetic operations like addition, subtraction, multiplication, and protected division. I also used unary functions like sine, cos, square root, log, negation, and many more. To allow conditional logic, I added an if-then-else function. A small random constant generator was also used to introduce more variation. Together, these functions give GP enough power to explore complex rules while keeping the expressions readable. So now, let us talk about the genetic programming setup that I used. I used a population size of 400 individuals and ran the evolution for 50 generations. The crossover probability was 0.5, meaning half the population mixes expressions. The mutation probability was 0.25, which helps maintain diversity. To prevent the GP from creating overly large expressions, I limited the maximum tree height to 14 and used a parsimony penalty so that the smaller models are preferred when accuracy is similar. The fitness function was defined as 1 minus accuracy, meaning the lower fitness is better. So all of these settings were tuned to balance the exploration, performance, and explainability. So now let us talk about the fitness and the training. So as I told you before, the fitness is 1 minus accuracy plus a small penalty size that is shown in the figure down. So during training, genetic programming works by evolving many candidate expressions over several generations. Each individual expression is tested on a training data, and we measure how good it is by checking how correctly it predicts the income labels. This becomes its fitness. The expression that performs better are more likely to be selected to create the next generation using crossover and mutation. Over time, the population improves because weaker expressions disappear and the stronger ones survive and combine. The search gradually becomes more stable as GP gets closer to a good solution, thanks to the design of the fitness function, which also includes a small penalty for very large trees. The evolved expressions stay simple and do not grow unnecessarily. This helps avoid overfitting and keeps the final model interpretable. After running genetic programming for 50 generations, the best model that GP discovered was a very simple and interpretable expression. The expression is if feature x48 minus feature x42 is greater than 0, then use feature x33. Otherwise, use feature x3. Let me explain this in simple words. GP evolved a rule-based mathematical expression. It first checks the difference between two input features, that is, feature x48 and feature x42. If the difference is positive, the model relies on a feature x33 to predict whether the person owns more than 50,000 or not. If the difference is not positive, then it uses feature x3 instead. We do not manually choose these features. GP automatically evolves and selects the features that give the best accuracy. The nice thing about this model is that it is extremely interpretable. We can clearly see how the decision is being made. Unlike black box models such as random forest or neural networks, even though the final model looks very small, it performs surprisingly well, giving about 82% accuracy on validation. This shows how GP can discover simple but powerful patterns in the data. So now let us talk about the results. The model achieved a training accuracy of around 82.76% and a validation accuracy of 82.57%. These results shows that the model generalizes well. It also outperforms the baseline GE model mentioned in the assignment, which had around 74% accuracy. On Kaggle, the model achieved competitive performances as well. The classification report showed strong performance on class 0 and reasonable performance for class 1, which is typically harder due to imbalance. Overall, GP produced a good balance between accuracy and interpretability. There are many ways this project can be improved in the future. One idea is to let the GP run for more generation or use a bigger population so it can search for even better solutions. Another option is to change or expand the function set so the model can learn more types of patterns. We could also try combining several GP models together like an ensemble to make the prediction stronger. Doing feature selection before running GP might help by removing unnecessary features. Finally, we could use multi-objective GP, which means the system tries to balance accuracy and simplicity at the same time. So now, to wrap everything up, this project showed that genetic programming can build a simple, clear, and understandable model for predicting income. GP didn't just give us black box result. It learned a rule that we can actually read and make sense of. With clean pre-processing, the right function set, and well-chosen parameters, the model performed really well on both the validation set and the Kaggle leaderboard. The best part is that the final GP expression is completely transparent, so we can clearly see how the model makes decisions. This makes GP a great choice when we want both accuracy and explainability. Thank you so much for watching the video till end. Have a great day.